Okay, so we have Thanksgiving tomorrow, which is great. And I don't know. Okay. Well, anyway, it's a good time. So enjoy your time with your family and the day off. We will have a test on Monday when you return. So not a surprise. It's just it's just there, right? So I thought I'd spend today, I guess, reviewing and going over some of the I guess finer points of hypothesis testing and confidence intervals. There will probably be a few questions, a few multiple choice questions that some might consider challenging, so I just want to make sure we have a good understanding of these topics here. Okay. Let me see if I can move this desk out of the way. The amount of furniture at the front of the room continues to amass. So. Yes, that's it. Okay. So let's talk about hypothesis tests. So again, with hypothesis tests, is that we observe a sample. Okay, so we observe a sample, and based on what we see in the sample, we want to know if does our sample refute an initial belief that we have about the population. Okay, so we have some initial belief about the population, which we call the null hypothesis. And we ask, does what we see in the sample refute contradict or go against our initial belief, our null hypothesis? And to answer that, we ask, well, how likely are we to see data that looks like our sample if the null hypothesis is true? So if our initial belief is true, how likely or unlikely are we to see our data? In this probability, what do we call this probability? The p-value. So this probability is known as the p-value. So the p-value is the probability of seeing data like our sample, or something more extreme, if the null hypothesis is true. And so based on this p-value, we make a decision. Okay? And so our decision is that if the p-value is large, then that indicates it is quite likely for us to observe our data when the null hypothesis is true. So, so on that, we don't have reason to reject the null hypothesis. We have reason or evidence to reject the null hypothesis. And if the p-value is small, it tells us that yes, it is technically possible for us to see our data, even when the null hypothesis is true. But it is unlikely. But it's unlikely to happen. So we choose to reject the null hypothesis. The criteria that we use to decide whether the p-value is large or small, what do we call that? The significance level. Okay, so we have something called the significance level, known as alpha, and that is what we use. It's our arbitrary line to decide whether the p-value is large or small. Most common choice for alpha is 5%. And we talked about type 1 and type 2 errors. Okay. We said the probability of a type 1 error is equal to alpha. And what was a type 1 error? Yeah.
That's when we fail to reject, that's when you reject A0 section true.
Yeah, so the type 1 error is the data has led us to reject the null hypothesis. Okay? But it turns out the null hypothesis is true. Okay? And this happens just every now and then because we might, when we do our analysis, it says, yeah, it's unlikely for us to see our data if the null hypothesis is true, but it's still possible. Okay? It's unlikely, and if it's unlikely enough, we choose to reject the null hypothesis. But it's still possible, and we end up with a p-value less than alpha percent of the time. And so we commit a type 1 error with probability alpha. Okay, so when we start our test, the probability of committing a type 1 error is alpha. And in contrast to type 1 error, we have a type 2 error. So a type 2 error is the data leads us not to reject the null hypothesis, but the null hypothesis is false. So it should have been rejected. And the probability of a type 2 error is beta. And we did not get into the calculations for beta, and that's okay. But you just need to know that the probability of type 2 error is beta. And the probability of the complement of a type 2 error, so 1 minus beta, is known as the power, which is the probability of correctly rejecting the null hypothesis when the null hypothesis is false. So, with all things being equal, okay, so if we just use the same data, okay, so we don't change anything, we use the same data, same hypotheses, increasing alpha will decrease beta, and decreasing alpha will increase beta. Okay? Or maybe I should say increasing alpha will decrease beta, which increases power. And decreasing alpha increases beta, which decreases power. So if we want to increase power, we can increase alpha, but that increases the probability of a type 1 error. So when do we want, so we get to choose whether to have a large alpha or a small alpha. When we start out a hypothesis test, we should decide what our alpha significance level is. Okay? If you're not sure, 5% is a good one to use, but there are some situations where you might want to choose a larger alpha, or there are other situations where you want to choose a lower alpha. Okay? So when would we want to pick a large alpha? Or when would we want to pick a small alpha? Okay. Well, you have to think about the cost of the type of errors. So we have a type 1 error and a type 2 error. And we have to ask, do we prefer to make a type 1 error in this situation, or do we prefer to make a type 2 error in this situation? Okay. So given a situation, here's an example. Okay. So think of a fire alarm. Fire alarm / smoke detector. Okay? So these are things you put on your ceiling. If the room fills up with smoke, it sounds an alarm, so you know that there's a fire somewhere. that either needs your attention or you need to evacuate. Okay, so the smoke detector has two jobs. One is very obvious, and what is its primary job? Okay, so when there's smoke, it needs to sound an alarm. And what's the second job? That's so obvious that we probably don't think about it. What's that? The second job is when there's no fire, it needs to be quiet. Okay? Now this sounds like it's obvious, and you don't think about it until something's malfunctioning and it's not doing that job. Okay, so in this case, imagine this were a hypothesis test. What would our null hypothesis and what would our alternative hypothesis be? Remember, we're gathering data to support the alternative. We never gather data to support the null hypothesis. So in this case, our null hypothesis would be what? There is a fire or there is no fire? There is no fire, okay? So the null hypothesis is that there is no fire, because the data that we gather is the presence of smoke, okay? So when there's smoke, that supports the alternative. If there's not enough smoke, then we have no reason to reject the null. So we're always gathering data to support the alternative. The alternative hypothesis would be there is a fire. Okay, so in the context of this problem, what is a type 1 error? Type 1 error is rejecting the null when the null hypothesis is true. So type 1 error would be?
There was an alarm, but there wasn't a fire.
Yeah, type 1 error would be what we call a false alarm. No fire, but making noise. Okay. And what is a type 2 error? Yeah, there is a fire. But it is silent. Now when you are a smoke detector company, you don't want to make either mistake, okay? You don't want your smoke detectors to be known to be sounding false alarms. You don't want your smoke detectors to be known for not sounding an alarm. But if you were forced to choose to make a type 1 error or type 2 error, if you had to choose which side to lean towards, which would we prefer to make? A type 1 error, okay? Because a type 1 error is annoying, but a type 2 error could be tragic. So in this situation, we would prefer to make a type 1 error than a type 2 error. Okay? If we were forced to make an error. So in this situation, would we want to choose a large alpha or a small alpha? Yeah, we would pick a large alpha, okay? Because increasing alpha would increase our risk of type 1 error, but it would decrease beta, the probability of type 2 error. So we pick a large alpha. Okay. And so that's why if if you install a smoke detector in the kitchen, sometimes it will go off if you're just cooking, all right? It's because they made them very sensitive so that it will sound an alarm if things get a little too hot. And you'd rather have that, okay? It's actually slightly reassuring when the smoke alarm goes off or the fire detector goes off if you're cooking in the kitchen, because you know at least it's working, right? Even if it's a little bit annoying that you have to reset it and things like that. Okay, so in that situation we would prefer a type 1 error, so we'd pick a large alpha. Can you guys think of a situation where you'd want a low alpha? Okay, so in our case, so I'll give you an example. Our justice system. Okay, and did you guys ever watch the show Cops? It's no longer on the air, but I don't know. It was like the predecessor to all these reality shows, right? And they would just follow a police squad, and then they would bust people allegedly breaking the law. Okay, but what do they say at the end of every show? Or did anyone ever watch this show, or am I like totally okay? So you guys at least have some familiarity. What do they say at the end of every show? Yeah, they say all suspects are presumed innocent until proven guilty in a court of law, right? So in that case, so that gives an idea to if we were to treat a court case as a hypothesis test, what would the null hypothesis and the alternative hypothesis be? The null hypothesis is that the defendant is guilty or the defendant is innocent. So the defendant is innocent, and the alternative is that the defendant is guilty. So we presume innocence unless the evidence leads us to believe the alternative. So it's the prosecution's job to present evidence to convince the jury that this person is guilty. It's not the defense's job to prove innocence, okay? Maybe in other countries the system is set up differently, okay? But I'd say in most Western countries it's set up this way. Okay. What would it mean to commit a type 1 error and a type 2 error? Yeah, so a type 1 error is rejecting the null when the null is true. So this would be convicting an innocent person. And a type 2 error would be letting a guilty person go free. Now, we don't want to commit either type of mistake, okay? In a perfect world, we would not make any type 1 errors, we would not make any type 2 errors, okay? But if you were forced, if you were going to set up a justice system and you were to say, would we prefer to make a type 1 error or type 2 error in this imperfect scenario? Well, at least the founders of our country, what did they say? They said, we would prefer to make a type 2 error, okay? We would rather let guilty people go free than to convict an innocent person. This is always up for debate, but this is how our justice system is set up. So we would prefer a type 2 error. Okay? And so in this case, what do we do? Would we pick a large alpha or a small alpha? Okay, so we would choose a small alpha. And they actually say this during court cases. Okay, they don't say you use a small alpha in your decision-making criteria, but what do they tell the jury? Yeah, they say beyond a reasonable doubt. They say make sure you are certain beyond a reasonable doubt that the defendant is guilty if you're going to arrive at a guilty verdict. Okay, so they want to make sure that you're not just like, it could be, and he seems kind of guilty, so we're going to say guilty. They want you to be certain beyond a reasonable doubt. And so, with our justice system set up this way, we are going to make more type 2 errors than type 1 errors. And sometimes that's disappointing for people because they don't get the closure that they might have sought. But that's how we have it set up, because in the grand scheme of things, we would prefer to make a type 2 error over a type 1 error. Okay? So this gives us an idea or some reasoning behind whether we want to choose a large alpha or a small alpha. Again, if you're not sure whether type 1 error or type 2 error is worse, okay, so in some situations, both errors seem to be kind of bad, all right? The rule of thumb is that alpha 5% is kind of a medium point. So, going into the test on Monday, you need to know how to do the hypothesis test, make confidence intervals, but also this background and conceptual information is also important. Okay, make sure you understand p-values and what those mean and how our decisions are made. Maybe just a quick review. The conditions so that we can apply the central limit theorem. What was the central limit theorem, anyway, to begin with?
When the sample is large enough, it becomes the normal distribution?
Yeah, the central limit theorem is that the sampling distribution states that the sampling distribution of p hat or y bar follows a normal distribution. When the conditions are met. And this forms the basis for all of our hypothesis tests and confidence intervals, because all of those numbers and the z-table we use assume that there's a normal distribution at play. But if these conditions are not met, the distribution of p hat or y bar does not follow a normal distribution, and so we can't come to the conclusions by following our process here. Okay. So the conditions are what? One is that the sample is selected randomly, okay? Sample is selected randomly and independently. And if you have two samples, both are selected randomly and independent of one another, okay? Independently of one another. Okay. Second condition is that our sample is not too big. The book calls this the 10% condition. Meaning our sample is not is less than 10% of the population. And lastly, we have the sample is not too small. This last condition looks different for categorical variables versus numeric variables. Okay. When you have a categorical variable, we're dealing with proportions. So we have the success-failure condition. Which states that n times p has to be bigger than or equal to 10, and n times q has to be bigger than or equal to 10. For a numeric distribution, it just has to be large enough. Large enough generally is samples of 30 or more. Unless the population itself is normal, then any size sample is large enough. So these are the conditions that need to be met to apply the central limit. Well, let's talk about confidence intervals also. So we've seen two types of confidence intervals for categorical variables in one sample. We have p hat plus or minus z star times the standard error p hat q hat over n. So we have two samples. The confidence interval is for P1 minus P2. so far we've only learned for one sample. We'll learn the case for 2 samples soon enough, don't worry. T star has degrees of freedom equal to n minus 1. If we, for all confidence intervals, these 3 are just all confidence intervals in general, if we're using the same data and we want to be more confident about our confidence interval capturing the true value of the parameters, if we want to be more confident, do we make our intervals wider or more narrow?
Wider.
We make them wider, okay? And changing the level of confidence, using a higher level of confidence, what number does it affect in these formulas? The z or the t, okay? These critical values, these are the only thing that changes when we change our confidence level. So, if we use the same data, to increase confidence, about capturing the parameter value, our intervals need to be wider. Only the critical value T star or Z star changes. And vice versa. If you're willing to be less confident, you can have a more narrow interval. So let's say we make a confidence interval for categorical variable one sample. Okay, this is for the proportion of, I don't know, households that own a pool. So your CI is from 16% to 28%. I'm making these numbers up, so don't. If you get actual values on this, that'll be good. Okay. So what is the proper interpretation for this confidence interval? Oh, let's say it's a 90% confidence interval. We would write, I am 90% confident that what? the proportion of households in the sample and the population, proportion where? That's proportion of households in the population. Our confidence interval is always about the population, proportion of households in the population that own pools, that own a pool is between 16% and 28%. Yeah.
By saying this, do you mean like I'm confident that 90% of population has the wait.
Okay, so here's a good, let's see, let's decide if any of these other interpretations are correct or not, okay? So would it be correct to say 90% of future samples will have a proportion, sample proportion, between 16% and 28% pool owners. Is that correct or incorrect? This is wrong, okay? Because the confidence interval is not about future samples. To do that, you would need to create a prediction interval, which we will not learn in this class. Okay, so this is wrong. I don't know what to how do I indicate wrong? No good. Okay. What about there is a 90% chance or probability that the proportion of pool owners in the population is between 16% and 28%. Is that good or no good? This is also no good. Okay, what's the problem here?
It's low that there's a 90% chance.
We're not checking for probability.
Right, okay. We don't know the proportion of pool owners in the population, but that is a fixed number, okay? It's some number. If we could freeze time and had unlimited resources to truly calculate this value, we could, okay? But there's no uncertainty about it. It doesn't care what our sample or confidence interval looks like. There's no uncertainty about this, so it's incorrect to talk about a probability about something that has no uncertainty, or a chance when we're talking about something that has no uncertainty. So all we can talk about is our level of knowledge, or our level of confidence, but not about the probability of the proportion. So these are common misinterpretations of the confidence interval. Okay. We could say if we follow the process of making a 90% confidence interval, then there is a 90% chance that our random sample produces an interval that contains true value of p, the population proportion. This statement is correct. Because here